Hello everyone, my name is KOTA ANUSHA and I'm a third year undergraduate student of the Department of Mechanical Engineering enrolled in its BTech course. My roll number is 22 ME29004. I am delighted to present this project alongside my teammates KARANAM AJAY KUMAR and PITANI BALAJI SATYA GANESH. Today we will be discussing a problem statement that involves designing and synthesizing a simulator for a garage door mechanism. This mechanism is unique as it avoids the use of prismatic or higher kinematic pairs and is designed to occupy minimal space when the door is open. In addition to solving the primary problem, we also explored additional ideas such as determining the lifting force, finding the ways to reduce it, and incorporating monitorization while retaining a manual opening option. Let us check the overview of the approach. To address the problem, we structured our approach in three stages. First, we focused on understanding the 4R mechanism. This type of 4R linkage is fundamental to our design as it involves our revolute pairs, making it ideal for the given requirements. Next, we synthesized a 4R mechanism using a overlay technique. This method allowed us to design a linkage system that aligns with the problem constraints and meets the required functionalities. Finally, we analyzed the motion of the design garage door mechanism. This step was essential to ensure that the mechanism operates as it intended and fulfills the criteria outlined in the problem statement. Now, checking for the Grashof condition. An important aspect of our analysis involved checking for the Grashof condition. This condition determines whether a 4-bar linkage can achieve continuous relative motion between its links. If the sum of the shortest and the longest lengths, that is S plus L, is less than or equal to the sum of the remaining two links, that is P plus Q, the mechanism is classified as a Grashof linkage, also known as a class 1 kinematic chain. In this case, at least one link is capable of making a full 360-degree revolution relative to the ground link. On the other hand, if the length S plus L is greater than the length P plus Q, the link is classified as a non-Grashof mechanism or a class 2 kinematic chain. Here, no link can make a complete revolution related to the others. This analysis helps us to identify the type of mechanism we design and as its operational capabilities. Now, my friend Ajay Kumar will take over the synthesis part.
Hello everyone, my name is AJAY. My roll number is 22 ME10042, studying third year mechanical engineering at IIT Kharagpur. Now I will be explaining synthesis part of the mechanism. Synthesizing a 4R mechanism by fixing ground hinges O2 and O4 in two configurations and finding hinges using overlay technique. We assume the door to be an extension of link series. By inverting the mechanism to the final position, we get O2 dash which revolves about E2. By intersecting vertical line and perpendicular bisector of line joining O2 and O2 dash, the position of A is known. In our case, we get the linkage to be double crank mechanism. The basic structure of required 4R linkage is shown below. Here we are considering O for BS crank. For obtaining link lengths to the required output, we mainly use SolidWorks software for synthesis. And for better understanding of 4R mechanism and simulation, we also visited the following website. Now let us continue in the following website. Now these are various parameters that we can change. Now let us change them according to our output. Now this is the final position of the door. And after animating it, and this is the initial position of the door. Now my friend Balaji will continue the design and analysis of mechanism.
Hello, I am Balaji. My roll number is 22ME10062. Today, we are going to study the motion of garage door mechanism in SolidWorks. First, we are going to make a 2D sketch of our required mechanism, and we are going to use that 2D sketch to create 3D mechanism of the linkages. And next, we are going to simulate that 3D mechanism in assembly. And finally, we're going to do motion analysis of that 3D mechanism in SolidWorks motion analysis. Okay, let's move on to SolidWorks software. Okay, as you can see, this is the 2D sketch of 4-hour mechanism that we have synthesized according to the required constraints, and this is a double crank mechanism. Just as the name suggests, we have 2 cranks in our design which completely revolve about the ground. Using this sketch, we have designed each part individually. As you can see, this is our ground with length of 20 mm, and this is our crank with length 40 mm. This is our follower or coupler. This is a L-shaped coupler with one of its length equals to 18 mm and another one is 21.4 mm. And finally, we have our crank of length 40.5 mm. Using mate option and assembly, we have connected or joined these parts together so that they will form a 4-bar mechanism with a double crank which do complete revolutions. So we have used this 4-hour mechanism in our garage door simulation. Let's move on to that. So this is the final assembly of our 4-hour mechanism to the garage door. As you can see, the base of our 4-hour mechanism is attached to the frame and the coupler is attached to the gate or the door of the garage. So when we give an input to the crank, the garage door moves accordingly. We can get a better visualize of it in motion study. Let's go. In the motion study, the input we are giving is given to the green crank at the surface. So let's see the simulation of it. We have a feature in SolidWorks that allows us to plot various things such as force, torque, acceleration, or linear velocity, angular acceleration, everything. We can plot with them with respect to time. So we can use, for example, to use this, we'll select displacement, velocity, or acceleration, and let us assume we want angular velocity of my second crank. So what I'm going to do is I'm going to select the angular velocity option and the space, the magnitude. Just click OK. Then I'll be getting the plot for angular velocity of my crank. So similarly, using this feature, we have plotted results of the torque or the torque of our crank. As you can see, there are 2 troughs in this graph. These troughs signify the dead center configuration of our mechanism. And we have plotted the linear velocity of our crank and the linear acceleration of our crank, the linear velocity of our coupler, the orange part, the angular velocity of the coupler, and the linear velocity, linear acceleration of the coupler is this. And the angular acceleration of the coupler is this. As you can see, this feature is very useful for not only plotting the graphs, but we can also trace the path. So let's go on to that. As you can see, this is a simulation of the tracing of the path. As you can see, this is the path traced by our garage door endpoints. These 4 points. 1, 2, 3, and 4. Okay, that's it for the SolidWorks part. Now, analysis of motion of the crank. As you can see, we have plots for displacement versus time, velocity versus time, acceleration versus time, and jerk versus time plots of our crank. That's it. This is the 3D analysis of our garage door mechanism. Next, my friend Anusha will take over.
Now, let us check the ideas for further improvisation. To improve the linkage mechanism, we can switch from a 4-bar to a 6-bar system. This will make a movement smoother with less noise and wear. Adjustable linkages will allow us the mechanism to fit the doors of different sizes and weights. Adding sensors will help detect obstacles and prevent damage. Rubber or plastic parts at the pivot points will make the mechanism quieter. We can also redesign it to be smaller so it can fit in the tight spaces and offer different panels and finishes to match home styles. These changes will make the system easier to use and more flexible. Thank you, Professor Anirvan Das Gupta, for this wonderful opportunity to enhance our skills in the Mechanism Sessions course and for guiding us in the right direction.